Hello everyone. In this video, I'm going to introduce my recent research using process-guided deep learning and data-driven modeling to improve the representation of soil and carbon in Earth system models and to explore key mechanisms underlying global soil carbon storage. For the background of my research, we all know that soil is a critical component in the global carbon cycle. It's actually the largest carbon pool of the terrestrial ecosystem. At the same time, we have observed soil as a huge carbon sink to sequester carbon dioxide from the atmosphere. Understanding the soil carbon distributions and stock is essential in understanding global carbon cycle and its feedbacks to the changing climate. Although soil and carbon is extremely important in the state-of-the-art Earth system models, there are tremendous uncertainties among different models. No matter when we are talking about the total stocks of global soil and carbon, the spatial distributions of soil and carbon, or the transient simulations of a land carbon sink. In the CMIP5, the difference on the estimations of soil and carbon stock by different models could be up to 6-fold. In the conventional practice of simulation modeling, actually we generally distill mechanisms that we observed as important in soil carbon cycle from local observations. For example, the photosynthesis that provides the carbon provides the carbon input, and the following input allocation process where the photosynthesized organic carbon is distributed into different depths of soils by plant roots. Meanwhile, we also know that decomposition process is important, where the soil and carbon can be decomposed back to carbon dioxide, and such processes can be strongly affected by local environment such as temperature and soil moisture, etc., etc. Also, the vertical transportation, such as freeze thawing processes in the permafrost and biotubation, are also important for the vertical exchange of soil and carbon among different soil depths. Finally, effects from soil microbes and minerals are being more discussed nowadays. For modelers, on the basis of the mechanistic understanding from local observations, we can abstract those mechanisms into mathematical equations. And by using the mathematical equations, we can simulate the target properties in soil carbon cycle, such as the distributions of soil and carbon and how it may respond to climate change to gain more understanding of carbon cycle in the global scale. In this process, as you may have already noticed, we have gone through actually several levels of abstractions from the field observations to the global understanding of soil carbon cycle. Actually, we are not sure whether the global simulations of soil and carbon are representative. This might be the main reason why, although we have so many complicated Earth system models, but hardly can we precisely estimate soil and carbon. Something has to be done to fix the absent connections between the model simulations and field observations. Actually, data simulation has already been proposed as a potential solution to this issue. In the previous unit of the training course, I believe you have already been familiar with data simulation. Here, I only briefly go through it. For a specific model, if we want to optimize its simulation performance, adjusting its parameterization may be a valid solution. The data simulation technique can help us automatically adjust parameter values by comparing the difference of model simulation from observations. Eventually, data simulation optimizes parameter values to where the model simulation best fit observations. We have already plenty of examples to show that data simulation does help model perform better in more soil carbon cycle simulation. But here I would like to point out that we still cannot count on data simulation alone to solve all the problems. From this figure, we can see that there is still, geographical biased representation on soil and carbon by model simulation, even after the, data simulation optimization. This actually arises a critical question, that is, how can we really best use the local observations to advance soil carbon studies? In the past years, we have developed a novel approach trying to address this issue, the so-called PRODA approach, of which the full name is process-guided deep learning and data-driven modeling. Integrates big soil data, data simulation, and deep learning to fully interpret the information hidden in the data, and strive for mechanistic understandings of global soil carbon cycle. Four main components together form the PRODA approach. The first one is the big soil carbon data that's collected from field surveys or experiments. The second one is the process-based model that describe soil carbon cycle by mathematical equations. The third one is the data simulation technique, and the fourth one is the deep learning algorithm. We will then discuss more details about these four components in the next few slides. For the big soil carbon data, we use the vertical soil and carbon profiles compiled in the WOSIS dataset. Taking the US continent as an example, more than 26,000 vertical soil and carbon profiles can be used in the PRODA approach. And at the same time, we also have the corresponding environmental variables such as temperature, precipitation, and edaphic features from other data sources. On the other hand, we use the matrix CM5 model as the process model to simulate soil and carbon. I believe you have already known the matrix representation of a carbon model very well after previous studies of in this training course. We can use this equation to easily calculate the soil and carbon stock at steady state. One thing I would like to remind you is that parameters in the matrix equation all indicate different types of processes in the real world, as I highlighted by different colors here. In the future, understanding processes in different categories will be the key to understand what observations have told us and how the soil carbon cycle will respond to climate change. After we have set up the big data and process model, the next step would be fusing the model with the data, that is the so-called data simulation. In a PRODA approach, we do the data simulation at each observational site to retrieve the optimized parameter values for that site. This procedure maximally utilizes the data information, but also leaves a caveat that we only have the site information and can hardly, upscale the site information to continental or even global scales. The deep learning algorithm is then designed in the PRODA approach to solve this problem. If you still remember For each site observations, we not only have the soil and carbon measurements, but also we have environmental conditions of that site, such as climatic and edaphic features. The deep learning algorithm applies those environmental variables to predict parameter values that are optimized in the site level data simulation, and then provide optimized parameter maps of the United continent or even the whole world. Eventually, we use the predicted parameter values by the deep learning algorithm in this back in the process model to simulate soil and carbon. The figure on the left shows the performance, how well the deep learning algorithm can predict the parameter values that optimized in the site level data simulation. And the figure on the right shows maps learned by the deep learning algorithm. If we apply the predicted parameter values by the trained deep learning back to the CM5, we can see the agreement between model simulation and observations can be as high as 0.6, which is much better than the batch data simulation. Batch data simulation. Actually, compared with the default simulation, the batch data simulation can improve the model simulation, but only to a limited degree. Product approach can help us to precisely describe soil and carbon distributions by the process-based model in the continental scale. To further illustrate the advantage of product approach, actually the upper panels of this figure present the spatial bias of model simulation by different methods. We can clearly see that if we take spatial constant parameter values across the continent as what have been done in the batch data simulation and the default model simulation, there will still be significant geographical bias even after optimization. However, if we take spatially varying parameter values, that is what we are doing in the product approach, the geographical bias will be mostly disappeared. In terms of spatial representation of soil and carbon, we can see from this figure that compared with the observations, the default model without any optimization strongly overestimates the soil and carbon. When taking optimized parameter values from a batch data simulation, we can capture some of the regional patterns, but not all the details. When we consider the varied parameter values in product approach, more details of soil and carbon distribution can be captured by CM5. If we look at the total soil and carbon stock of the US continent, we can actually see that the default model, severely overestimates soil and carbon stock from the surface to the deeper soil layers. The batch data simulation can effectively constrain the total soil and carbon stock to a reasonable level. Although as we discussed in previous slides, they can call batch data simulation can cause spatial bias. But at the same time, the product approach, of course, gives the estimations that is most close to conventional estimates along the soil depths. When we further look at the soil and carbon stock in different ecosystems, we can actually see that for batch data simulation, it presents soil and carbon distributions very well in cropland, but have underestimations in grassland, wetland, and evergreen forest. The product approach, in contrast, performs very well in all ecosystem types. So we have just discussed the first applications of product approach. We find that compared with the default model parameterization, the optimized parameter values by data simulation can correct the enormous bias by soil and carbon stock estimation in model simulation, but may not be able to describe spatial details of soil and carbon distributions. To further improve model simulation, the product approach predicts spatially varying parameter values with environmental variables and achieves the most precise representation of soil and carbon distributions in CM5. Actually, product can do much more than improving model simulation. When we extend the big soil data to the whole world and apply product approach again, we can also explore the key mechanisms underlying global soil and carbon storage. We can see that actually product first helps precisely describe soil and carbon distribution at the global scale, of course. CM5 cannot explain 56% variation of soil and carbon and gives estimations of total global soil and carbon stock that are very close to inventory sources. For the whole soil profile, the global soil and carbon stock is about 2,400 petagram carbon. For the first meter soil, the number is about 1,300 petagram carbon. Apart from that, from the right panel, we can also get the global distributions of resin time of soil and carbon. More than the resin time, actually product can help us get specific ecosystem level mechanisms underlying global soil and carbon storage. For example, we observe microbial carbon use efficiency is higher in boreal regions than that in tropics, and the plant roots can reach deeper in tropics than that in boreal regions, as indicated by the higher input allocation index. For the decomposition processes, we can know that actually the substrate is more decomposable in the boreal regions, as indicated by higher baseline decomposition index. But at the same time, the real decomposition rate is also regulated by physical environment. The environmental restrictions on decomposition in boreal regions is much larger than that in tropics, as shown by the lower environmental modifier index. At the same time, we can see that actually all the mechanisms present the spatial variability. So a question naturally arises is that how will such spatial variability of mechanisms influence the global soil and carbon distribution pattern? Following this question, we further use the product approach to conduct a sensitivity experiment. When the spatial variation of one mechanism is ignored, how will the final soil and carbon be affected? The result shows very clearly that the spatial variability of carbon use efficiency is the most important to both global soil and carbon stock and its spatial distribution, spatial patterns. We can see from this figure actually when ignoring the spatial variability of carbon use efficiency, the final simulation will deviate most from our best estimates by the product approach. The importance of carbon use efficiency can also be verified by the sensitivity curve of soil on carbon. When we assign a +1% change to all mechanisms, changes of carbon use efficiency will lead to the most strong response of global soil and carbon storage. If we put such a sensitivity curve in a specific context, for example, increasing global soil and carbon storage 4 per mil each year to mitigate the climate change, actually the increasing carbon use efficiency is apparently the most plausible solution. Only 4% increase of carbon use efficiency from its current value is required to achieve the 4 per mil target from now to 2050. But the question is, how likely can we really manipulate carbon use efficiency to achieve such ambitious target? We may first understand which to answer this question, actually, we may first understand which factors are controlling the value of carbon use efficiency. Proda also gave the answer. Part of the answer, actually, we find that for all the environmental variables, we can possibly propose soil or physical properties are the most important to the spatial patterns of carbon use efficiency. If we look into the details, we can tell that actually managing the soil into lower bulk density, more aggregated loam will be best favor the increase of carbon use efficiency. But at the same time, we must admit that such understanding is still far from enough to achieve such kind of ambitious target. In the future, we must explore more detailed mechanisms by field experiments and observations. To conclude, in this lecture, we introduce the Proda approach as a powerful tool to integrate big soil data with process models to precisely simulate regional and global soil and carbon distributions. And at the same time, Proda also provides the opportunity to explore key mechanisms underlying global soil and carbon storage. We identified carbon use efficiency as the central mechanisms in comparison with other mechanisms such as carbon import and decomposition in global soil and carbon storage. And in the future, more exploration is desired to understand more detailed processes underlying carbon use efficiency. Before the end of this lecture, actually, I would like to further discuss a little bit on whether on a question that is, when we are talking about the Proda approach, what are we really talking about in terms of how to get the realistic simulation in the modeling community? For a long time, modelers will use meteorological data to drive the model simulation, where the model structure is and parameterization have already been fixed based on our empirical understanding. This approach is totally based on our process understanding of land carbon cycle and does not take information from the data. At the same time, there is another extreme on this spectrum, that is digital soil mapping, where scientists do not consider processes in land carbon cycle, but only focus on the data they can get by applying techniques such as deep learning. They want to represent soil and carbon distributions as close to the observations as possible. In this polar, we only focus on how to mine desired information from the data. The process-based, the so-called ad hoc parameterization and statistical data mining are the two extremes of the spectrum when we want to understand land carbon cycle. Throughout the second part of this training course, I believe you have learned how to use conventional data assimilation to improve models simulation performance. We call this as the the process-based data-driven parameterization. You can see that on the basis of a traditional simulation modeling, we are now considering using data to infer the parameter values. But soon we found that for simulation at the continental or global scale, conventional data simulation may be not enough. The spatial heterogeneity of processes in soil carbon cycle, which represented by parameters, should not be overlooked. Therefore, we proposed to take the advantage of data mining techniques to further explore such spatial heterogeneity of parameters. We call this as the process-guided deep learning and data-driven modeling. That is the so-called PRODA approach. The PRODA strikes at the balance point of between process understanding and data mining to optimize model simulation. Specifically, it combined the process-based model, the observational data, conventional data simulation method, and deep learning algorithm to best optimize model simulation, and more importantly, to explore land carbon cycle mechanisms and its response to climate change. So in the next practice session, I will introduce the product with more technique details, especially the deep learning part, to help you to operate it. So here is the very end of this video. If you have any questions, please feel free to ask in the Slack or directly contact me by email. Thank you.